All right, this section we're going to be looking at rates and proportions. So to start off, a ratio is a comparison of two numbers or quantities. With a ratio, they are measured in the same or similar units. Ratios are always written in the smallest terms. So for example, the ratio of adults to children at an elementary school is 2 to 5, meaning that for every 2 adults there are 5 children. So if there are 50 children in attendance, how many adults are there? So the ratio is 2 adults for every 5 children. We have 50 children. So that's 5 children, 50 children. So that's 10 times the number of children in the original ratio we were given. So that means there would be 20 adults present. Ratios can be written 3 ways. This first ratio, I could have written it as 2 to 5, 2:5, or as a fraction 2 over 5. But both of these, all of these, this first ratio was talking about the number of people. So that's, the unit is, children to adults, we're looking at the number of people. A rate is a special type of ratio that compares two quantities measured in different types of units. So instead of having the same unit on top and bottom or a similar unit on top and bottom, we're looking at different units. So for this example, water is dripping out of the sink at a rate of 2 liters every 3 hours. Write this out as a rate. So to write this as a rate, we would say 2 liters every 3 hours. I'm just going to rewrite that line. So it's 2 liters every 3 hours. A unit rate is a rate with a denominator of 1. So if you simplify that, where the denominator becomes 1, then you have a unit rate. So for this example, Sheila drove 65 miles per hour. As a unit rate, your speed in miles per hour is a unit rate. It's telling you how fast you're driving in 1 hour, per hour. So the unit rate here is 65 miles every 1 hour. We can also use unit rates in our everyday lives when we go to the grocery store or the hardware store or literally any store, anywhere where you buy things in large quantities. So this example, we are going to look at different jars of peanut butter. 1 jar of peanut butter gives us 16 ounces, and it's going to cost $2.49 for that jar of peanut butter. There's a larger jar, it's 40 ounces, and it costs $5.99. We're going to calculate the unit rate to determine which jar of peanut butter has the cheaper unit cost. So which one costs less for each individual ounce of peanut butter. So we're going to calculate the unit cost. Okay, I'll put we're going to find what's called the unit cost. And some stores, like King Soopers, does a really good job of actually putting this on their tags. Other places like Walmart, they don't, and Walmart actually is very sneaky about how they do this, about how they price things, and they'll make you think that you're getting the better deal on the thing that says, value pack, when you're not. Also, King Soopers, even though they do this, sometimes it's not the same units. They'll put one thing in terms of ounces, but then the other thing will be in terms of the number of items in the box or something. It's not always the same. So you do have to be careful about that when you look at King Soopers as well. So let's look at the 16-ounce jar first. So to find the unit cost, what we want to calculate is the price per ounce, The word per in this case means division. So we're going to take the price and we're going to divide it by the number of ounces we get. It's the price for each ounce that we're buying. How much does it cost for each ounce that we buy? Price per ounce. So the price is $2.49. And for that $2.49, we're going to get 16 ounces of peanut butter. So $2.49 divided by 16 is 0.16. We're talking about money. This is the price per ounce. So for 1 ounce of peanut butter, you're paying approximately 16 cents. Okay, let's write that out. 1 ounce of peanut butter is going to cost about 16 cents in the 16-ounce jar. Let's compare that to the 40 ounce. Oopsies, 40 ounce. So the 40 ounce is $5.99, but we're getting 40 ounces. So $5.99 divided by 40, and that rounds to about 15 cents per ounce. So it costs 1 ounce of peanut butter from this jar is going to cost you 15 cents. So it doesn't look like a huge difference, but think about how much peanut butter you might buy in a month, okay, or over your lifetime. That could end up being a very big difference when you think about how much peanut butter you're buying overall. So the 40-ounce jar is the better option because the price per ounce is cheaper. And just so you know, these are actual prices of an actual brand of peanut butter. It is the same brand. Okay, I'm not comparing generic to non-generic here. It's the same brand, just different size jars. These are real numbers. I actually went to the King Soopers website and looked this up. Fun fact. Okay, so a cheaper cost for each individual ounce is what you're looking for. Because why do I want to spend more money on the same product? I don't. Okay? This is not always the case, by the way. The larger container is not always the better price. That's why you got to be careful, especially at Walmart. Walmart likes to make the smaller items cheaper. I don't know why, but they do. They think they're getting ya. Anyhow, I do this a lot when I'm at the grocery store. If I'm looking between two different sizes of something, I'll just pull out my phone and I'll calculate which one is the cheaper one. Okay, I did this with protein bars once. Okay, they had the pack of protein bars on the shelf, and it was like a multi-pack versus like buying the individual bars. It was cheaper to buy the individual bars and not get the 6-pack. So I bought a bunch of individual bars that I then had to scan each one individually because it was cheaper than buying the box that came with like 6 or 8 or something when I priced it out to how much it would be for each individual bar. So there you go. You can shop smarter if you weren't already doing this. Okay. A proportion is an equation of 2 equivalent rates. So an example, a 10-pound bag of M&M costs $8. How much does each pound of M&M cost? So a 10-pound bag is $8. We can set this up as a proportion to figure out how much does each pound, okay, I need to put units on here. Wait. pounds. I set this up wrong anyways. $8 for 10 pounds equals how many dollars for 1 pound? When you have two rates that are equal to one another, this is called a proportion. That's what I've set up here, is a proportion. What I don't know is the answer to my question. But we can find that. $8 divided by 10 pounds. 8 for 10, yeah, divided by 10. 80 cents. So it's $8 for 10 pounds, and that's equivalent to 80 cents for 1 pound. Again, this is a proportion. I have two rates that are equal to one another. Another way that I could have solved this is using what's called the cross product principle for solving proportions. So this says if I have two proportions, A over B, and that's equal to the proportion C over D, what I can do is I can cross multiply A times D, and I can multiply B times C. So what I end up with is A times B equals C times D. One of these, A, B, C, D, one of those will be unknown to me, but then I can solve for the missing value to figure out what it would be. All the other three of these letters will be known to you. Only one of them will be unknown. So we can solve for X, solve for the missing value. I could have done that with example 5, but I didn't, because I didn't need to. So here we have a proportion, 10 over x equals 2/3. What would be the value for x? We're going to solve that using cross multiplying. So I'm going to do 10 times 3, and I'm going to do x times 2. So 10 times 3 equals x times 2. So I'm going to simplify this. 10 times 3 is 30. And that equals x times 2. I'm going to write this as 2x just because that looks a little bit cleaner. So 2x, I want to have just one x, so I'm going to divide both sides by 2. $30 divided by 2 is 15. X equals 15. And you could check this if you do 10 over 15 in your calculator, 2 over 3 in your calculator, they should be the same decimal. That's one way to check it. Second one, negative 3 over 8 equals 6 over what? Totally fine that we have a negative here, not a problem. So I'm going to cross multiply again. So negative 3 times x equals 8 times 6. Just going to clean this up. Negative 3x equals 8 times 6 is 48. So negative 3 is in front of the x, so I can get rid of that by dividing both sides by negative 3. Not just 3, I have to do negative 3. Otherwise, I'll still have that negative in front of the x. So 48 divided by negative 3. So those go away. X equals negative 16. So a couple of simple examples of cross multiplying for proportions. But now we're going to look at a couple of more complicated ones. These are ones where you're going to be looking at a scenario and you have to figure out how to set up the proportion and then solve for it. So for this one, An object's weight on the moon is proportional to its weight on Earth. Neil Armstrong weighed 360 pounds on Earth when he had all of his equipment on, and 60 pounds on the moon. What would a person weigh on the moon if they weigh 174 pounds on Earth? So we're going to set up these proportions. It doesn't truly matter too much how you set this up, but you have to be consistent. So what I'm going to do is I have information on Neil Armstrong. I know how much he weighed on Earth, and I know how much he weighed on the moon. I'm going to set that up as my first ratio, my first fraction. I'm going to put his Earth weight on top and his moon weight on bottom. Doesn't matter. I could put the moon weight on top and the Earth weight on bottom. Doesn't really matter. And then that's going to be equal to, now we have this other person. What would a person weigh on the moon if they weigh 174 pounds on Earth? So this second person that we have, we know how much they weigh on Earth, and the Earth weight went on top, right? So I put the Earth weight on top, and I put the moon weight on the bottom. What we don't know is how much would they weigh on the moon. That's what it's asking us to find. What would a person weigh on the moon? That's our unknown. That's our X. What you have to be consistent about is Earth weight on top, moon weight on bottom. I can't flip-flop this one. I can't do X over 174 because that's going to mess it up. I put Neil's Earth weight on top, so I have to put the second person's Earth weight on top. And then the moon weights go on the bottom. That has to stay consistent. Whatever you put on top has to stay on top. Whatever you put on bottom has to stay on bottom. So then I'm going to cross multiply. Boop, 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 boop. So 360 times X equals 60 times 174. So clean this up. 360x equals 60 times 174 is 10,440. And we have 360x, but we only want 1x. So divide both sides by 360. And we get x equals 29. And we do have units here, so it's 29 pounds. So they would weigh 29 pounds on the moon. So another one, I think this is the last one. Yep, this is the last one. To estimate the number of bass in a lake, wildlife biologists tagged 75 bass and released them back into the lake. Later, they caught 124 bass and found that 40 of them were tagged. Approximately how many bass are in the lake? So they initially tagged 75 bass, and then later they caught 124 and found that 40 of them were tagged. So they tagged 75 out of, I don't know how many. How many bass are in the lake? I don't know. Maybe? And then later, they found 40 tagged bass out of the 124 that they caught. So I set this up as tagged over total. So 75 out of all of the bass were tagged the first time, and then 40 out of the 124 that they recaught were tagged. So I'm going to cross multiply again. $75 times 124, x times 40. $9,300 equals 40x. Divide both sides by 40 because we want just 1x, not 40x. And we get 232.5 equals x. But you can't have half a bass because that's what we're trying to solve for. We're trying to answer how many bass are in the lake. You can't have half a bass. So the answer to this one is going to be 233 bass. You have to round this one up to a whole number because you can't have half of a bass. So the tricky thing with these is getting it set up, but just make sure you stay consistent. If you put tagged on top, keep them on top. If you put the earth weights on top, keep those earth weights on top. And those are unit rates and proportions.